All right, Bill. Thanks for coming. Let me say a few words to kind of set up our conversation. So, as uh, as you know, I'm a mechanical engineering professor, and just because we're mechanical engineers doesn't mean we don't use computers or sensors or actuators or electronics. And one thing that's become very popular in the last couple of years, I think for many practicing engineers, is something like this. This is the Arduino Uno. You know, $20. It's got, for your information, it's got an ATmega 328P, which is an 8-bit microcontroller that's running it, and peripherals and et cetera. And and I think that as mechanical engineers, we're sort of end users, right? We use this to control robots or automation or whatever it is. In terms of engineering practice, we're using this, and the way we use this is we code it in, specifically this one. We code it in a C-like language. Let me just show you the IDE just for your own perspective. So this is a blank IDE. Can you see it, Bill?
Yes, I can.
So here you have you have your initialization code, and then you have a code that loops, and there's many other functionalities, but that's sort of the starting gist of it. And the one thing you do is you write your code, and then you hit the compile button, the compile and upload button. And one thing I've been thinking about is it'd be nice to have a conversation about what is going on. When you hit that arguably for many of us it's a magic button, but for many of us like you, it's not a magic button. You know intimately what's going on. And of course, so that's what I want this conversation to be about, kind of. And also, of course, I could Google a lot of this information. There's a lot of great information out there, but you've been doing this for many years. In fact, I pull up your web page here. And I think that more than just here's all the compiler stuff that you've done, and more than just the answers to these questions. What is a compiler? What's going on? But also, it'd be great to hear the history that that's one thing you're not going to get on Google is that. So that's kind of my idea of this conversation.
Okay. Well, I can go back to origins. I was born in New York City, 1939, and after the World War II, we moved back to the city. My dad was in the Army, stationed at the Pentagon, but we moved back to the city, and one of the things that I loved to do was ride the subway. And my dad would take me and sit me on the brake wheel at the front of there was actually a brake wheel in the passenger's compartment, the front of the train, so we could see what was happening. Now, at 96th Street and Broadway, there was a split between two lines. One went up to Van Cortlandt Park, one went up towards the Bronx Zoo. And I was fascinated by the switching. Yeah. Switching the trains, because expresses came up and they switched onto the local tracks and went up through our neighborhood, and locals came up and they switched onto the express tracks and went down into the tunnel. That just fascinated me. So I was always drawing diagrams of how that would happen. And then our apartment got an automatic elevator. And I was fascinated with how the automatic elevator worked and what sorts of things were. When I got to high school, I actually turned this into an interest in switching theory, which is what was called then, how you use relays to control this stuff.
And relays meaning electromechanical relays.
Electromechanical relays. Yeah, no, there was no such thing as, at least in the common parlance of
Right.
as like the Arduino, of course.
Right.
So I got into switching theory and minimizing switching circuits and so on, and did some of that as I was in college. And when I was in college, I met a really nice lady, and I got engaged to her. And so I was going to go to graduate school, electrical engineering, and she was going to support us in the style to which we had become accustomed. Well, she was a math minor, and so she submitted her applications for math jobs. She was a physics major, physics jobs. And back in those days, women were not particularly welcome.
Okay.
So she interviewed with a firm called Mutual of New York, who's an insurance company. And the guy said, well, you know, we don't have any actuarial positions, but how would you like to be a programmer?
Oh, cool.
And she said, programmer?
Right. What does that mean? Yeah.
Yeah. And well, I knew a little tiny bit about computing, but anyway, we graduated, we got married.
Where'd you go? Sorry, where'd you go to school?
Oh, I was at college at Oberlin, Ohio, Oberlin College. And then I went to Columbia University in New York for graduate school.
Okay.
And so during the summer before I actually entered graduate school, between college and graduate school, she went to school with IBM to learn programming.
Whoa.
And she brought back these fantastic stories about the things she was doing. I thought that was really interesting.
Yeah.
So I signed up. I was basically interested in control systems because of my switching theory background and my control of the elevator and so on.
Right.
And so I was, headed for that major. But she and I together took a course on Fortran.
Okay. So wait, if you step back, what did programmer mean at that time? What did your wife learn to do? Was there mainframe or what exactly?
Okay, this was in 1960.
Okay.
And yes, she was learning to program an IBM 7070.
Okay.
Which was a commercial mainframe.
Okay.
And she was doing systems programming. She also learned to program a 1401, which was a satellite processor that they used to do input and output. They had magnetic tapes that they would load up from cards on the 1401, and then they put the tapes on the 7070 to actually do the day-to-day, what they called the daily cycle, which was the stuff that they had to do every day to support the insurance business.
Okay.
Well, so I took this Fortran course, and then the Department of Electrical Engineering got an IBM 1620. So I took an assembly language course in the spring of 1961. Now the 1620 was a pretty interesting machine because it was character based, and it did arithmetic using lookup tables.
Okay.
So you had to load.
Well, I get trig with
no,
lookup tables.
Addition
and subtraction using lookup tables?
Yeah.
Okay.
The hardware would actually look it up.
Okay.
So I got interested, of course, in this, and this is down at the bit level.
Yeah.
And the interesting thing was to build a loader.
Okay.
Because what the machine did was you put a bunch of cards in and you pushed a button and it read those cards, and those cards taught it to load something else, a program.
Mm-hmm.
Now
and this was cards, so you're saying punch cards. We were doing
punch cards, yes.
Yeah, right.
Punch cards, yes. Mm-hmm. Yes, 80 column punch cards, standard punch cards.
Yeah. Oh yeah. Actually, here.
Yep, that's the one.
Yep.
That's the one.
Yeah.
That's the one. And so you had to punch the tables into those cards. Well, of course, that took quite a few cards, and the game was to get the smallest loader that you possibly could.
Is that mechanical? A mechanical? You're meaning a mechanical loader?
No, a program.
Okay. Oh, the program. Okay, got
The
it.
card deck that it read in had to be a program, and it had to have these tables in it.
Okay.
Okay, so that had to be basically programmed a bit at a time.
Wow.
Anyway, that was a kind of an interesting thing, and you could
Really
sit
cool.
at the machine, and you'd load your deck in, and then you could step through it and look at the lights, and so just like a debugger today.
Wow.
Your IDE.
Right.
Okay, we had our IDE was the machine console.
Right. And lights.
Yes, and lights. One of the things that you had to do was to clear the machine. Okay, so there were some instructions you could use to clear out the contents of memory. Mm-hmm. And as you sat at the console and watched the lights, you could see the memory addresses changing as it cleared out the memory.
Yeah.
Okay, so over the summer, they increased the amount of memory from, get this, 20,000 characters.
Okay.
To 60,000 characters, which was the maximum the machine could deal with.
Okay.
Okay, now if you're thinking about this, this is 60K bytes. And it wasn't K, it was 1,000, all right, because the addressing was decimal.
Okay.
Compare that with anything these days. What does that Arduino have on it?
60. Oh, yeah.
Memory?
Yeah, I'm not sure.
You're not sure, but it's a hell of a lot more.
Yeah, it's way more than 60. Yeah, exactly.
Right.
Wait, so 60 kilobytes, you say that's not how you say it, though?
No, it was 60,000. Because if you say 60K, that means 60 times 1024 binary.
Right. Yeah. Oh, I see.
But this was decimal addressing. So
right. So it's exactly 60,000.
Yes.
I'm with you.
Yeah. Okay. So I got back from the summer and sat down at the machine and cleared it. And there was something funny going on with the lights. There was just a gap somehow. They weren't progressing correctly. Well, we didn't think too much about this. And we had Fortran programs running and so on and so on and so on. And this went on until almost Christmas vacation, when somebody discovered that their Fortran program suddenly didn't work. What was discovered, what we discovered was that when they installed these extra units of memory, from essentially 1 unit of 20,000 to 3 units of 20,000, they hadn't wired up the middle 20,000.
Oh, no.
Yes. And the way Fortran worked was the program was stored up from the bottom of memory, and the data was stored down from the top.
Oh, so it never
actually got into that middle 20K until December, when somebody's program was big enough.
Right.
Okay.
Yeah.
Okay. So we had an assembler. We had a compiler.
Right.
The way it worked was you punched your program into cards.
Right. And let me say, when you say you punched, like you said, you punched your ASCII, for example, this represents ASCII, for example, right?
Yep.
No,
actually it represents EBCDIC.
Okay, all right, so that was before ASCII?
Well, yes, ASCII, that's right. And it only had capital letters.
Okay.
And digits and some punctuation characters.
But it was 0 to 255, kind of, or 128, 127.
Well, not really, because the card, the column of the card represented a character.
Right.
And the bottom part of the column was the numeric part, which would code character digits from 0 to 9, and the top rows of the column were the zone bits.
Right.
And so if it was a 0, 0 in the zone, it was A through I think it was, or A through H. And then if there was a 1 bit there, it was J through, anyway, it was a code. It was not a binary code directly. It was binary, but it was coded as these digits in zone.
But what I'm saying is it was an instruction. It was not a what's, I guess the lowest level is to access a place in memory and put in a binary number that represents an instruction, right?
Well, yes, but in that case, it wasn't a binary number. It was a sequence of characters that represented an instruction.
Okay. And that's what this card was. It was an instruction. This
card contained an instruction.
Okay.
Now when you punched it in, it was a Fortran statement.
Okay. It was Fortran. It was
Fortran statement. Yeah.
I see. Okay.
So what you did then, after you'd gotten this all punched up, the program, you would take the cards and you put them into the reader.
Yep.
And the compiler would read them, and it would punch out more cards.
Oh. Okay. Wow. Okay.
Then you would take the second set of cards and put them in.
Because that was so. Would those be the machine code cards?
No. Then you in the second run you actually got another deck out, which was the machine code.
Whoa. Okay.
The things that were printed out or that were punched out were an intermediate form of the program.
Okay.
So what the compiler, if you think about it, you have to have a sequence of instructions.
Mm-hmm.
That sequence of instructions is in successive locations.
Memory locations, yep.
Memory locations. But then you have conditional instructions, right?
Mm-hmm.
That have to transfer control to some other set of instructions.
Right, to memory or...
That's right.
Mm-hmm.
And so if you were writing a program directly in machine language,
mm-hmm.
you would have to put in all of those addresses for the jumps.
Right, which is a lot.
Well, it's
complicated.
It's not so much that it's a lot. It's that if you change the program by changing the number of instructions, that all the addresses change.
Oh, right. If you add a new instruction, right, you now want to do something else, everything else needs to rechange. So this is where the compiler.
Yes, that's what happened. What happened. You punched out this intermediate code, and the compiler was doing was it was calculating all the addresses and keeping that table in memory.
Okay. Yes.
And then when you fed the intermediate code back,
into the compiler again,
the addresses.
But then so you fed it back into the compiler. So the compiler has to know which deck it is.
That's right.
Okay.
That's right. So it was a several pass process.
So where does so Fortran is a high level language, what we would call high level.
Right.
Let's say similar to C or whatever, the way we think about it now.
Yep.
So where does assembly come in? Assembly language.
Okay. Remember I told you about the loaders?
Yes.
We wrote those loaders in assembly language.
Okay. So I see.
Okay, so the assembly language allows you to write a sequence of instructions.
Right.
Now, if you were writing in machine language, you would have to fix the addresses.
Right.
In the assembly language, you can use symbols for the addresses.
Okay. Why not?
So Go ahead.
Well, why not? What about writing, instead of writing in Fortran, write your program in assembly then?
You could do that. But if you look at one Fortran statement, that Fortran statement might translate into 8 or 10 or more assembly language instructions.
I see.
So when you write in Fortran A equals B plus C times something or other, then that that is expression which you can write on one line easily and you can understand.
That's right. It's like
Turns
human
into a
language.
whole sequence of assembly instructions which involve loads and stores and arithmetic instructions and conditional instructions, and you have to know all that. Whereas
Right.
if you write in Fortran, all you have to know is algebra.
Right. Right. So it's you're just going deeper into the into the whole.
That's correct.
Okay.
That's correct.
Okay.
That's correct.
And machine language is the lowest level.
Machine language is the lowest level. That is just the bits.
Right. Right.
And so you have to get those bits somehow. And of course, me having my background in switching theory and in, by the way, at this point, I had decided that control systems were way too many polynomials having to be factored.
Okay. Yes. Yes.
And so I said, no, this is not for me. I'd get into this computing business.
Right. Forget Laplace. You don't need Laplace for what you're doing.
That's right. That's right. That's right. So that's where I went. And as I say, because of my initial work with the 1620 and the loader and the arithmetic tables and so on, I was fascinated by exactly the process you were talking about, namely, how do you make these things, these computers, more available to people.
Right. To mechanical engineers, for example.
To mechanical engineers.
Right. Yeah. It's interesting, though. I feel like we're getting so far removed, which is part of why I like this, because I'm sort of, I'm a control guy too. And I like and I do digital. And so I'm in this sort of in between electrical and mechanical and mechatronics maybe. And I really do like to understand it, because I feel like at some point you're just trusting, you know, there's a lot of disconnects is what I feel like.
There is. And if you think about what's happened recently with these cyber attacks,
yes,
you have to trust this tool chain,
right,
not to do something bad along the way.
Right. So knowing, that's why I like to know a little bit lower level, not only because I think you can also, there's things you're not, for example, a general user of the Arduino, there's peripherals functionality that a general user of the actual processor that they're not taking advantage of because it's not available on this. It's not available on the board, but it is available on the processor. So from that perspective too.
Yes. Well, of course, that's the library issue.
Yeah.
Where you have a lot of stuff that programmers have written that you make use of.
That's right.
And as a matter of fact, on the 1620, we did have a library for doing things like sines and tangents and whatever. And when I finished my PhD at Columbia, I went to Australia for a year on a National Science Foundation postdoctoral fellowship to the University of Sydney, and they didn't use cards.
Oh.
They used paper tape.
Paper tape. Okay.
Paper tape. Now, think about the difference there. When you want to modify your program on cards,
you can just
pull a few out. Put a few in.
That's right.
Can't do that with a paper tape.
Well, although I've heard horror stories about dropping your cards.
That's right. That's
so
right.
With the tape, you're not going to lose your.
Oh, no. Wait a minute. Wait a minute.
Okay.
When your program is a tape that's that big.
Yeah.
And you're not careful holding it, the center can fall out.
So you got to roll it back up?
Well, yes. But the trouble is that when the center falls out, you've got a real rat's nest.
Okay. That's true.
What the physics building, which is where the computer was in Sydney at the time.
Right. And that's the other thing. Historically, there was like one computer, right?
That's right. That's right. But they had it was a very long building. And so some people, when that happened to them, they stretched the tape along the hall, the corridor,
Yeah.
and then rolled it up.
It's like the Hall of Shame, you know?
Yes,
Yeah.
yes. Well, but it's just like what happens when you drop your cards. And one
Yeah.
of my friends went to school in Boston, and he
Okay.
dropped his cards as he was getting off the subway. So
Oh
half of the cards
no.
stayed in the subway.
Oh no. That must have been awful.
Yes,
Actually,
yes.
actually, I've very minor story that's related to all that. Is when I was an undergrad, and I remember I was writing this 30-page, mechanical engineering lab report, mechanics and materials lab report, and I was sitting in the computer lab, and this was in the the late 90s, and it turns out back then Word didn't. I was using Word. It didn't autosave like it does now. So, and it just so happened, and I don't understand the logic, but the power strip was underneath the desk, and I hit it with my knee, and
Oh,
the computer just went black,
yep.
and and it was all gone. It was all
Yeah,
gone. And I mean, of course, I'm to blame for not saving or whatever. But anyway, I had a
yeah. Well, it's the same. It's the same thing. I mean, no
same
matter what the
concept,
medium, no matter what the
right?
situation is, you got to back things up.
Yeah. Although I will say these days, right? I mean, there's
Yeah,
a lot of.
yeah,
I
but
mean,
there's a lot of people who don't back stuff up,
right, right. Yeah,
and
exactly.
then they get in trouble just the same way.
Yeah,
But when we use these big paper tapes, and the programs did get big,
yeah.
we had an optical reader.
Hmm.
Now the operators, of course, were the ones that used it most of the time. But what
So
this thing
optical
did,
reader, a light, and a detector of some sort.
that's right,
Mm.
that's right, and the tape would shoot through it at about 1,500 characters per second.
Hey, that's
So
pretty good,
it was moving fast.
right?
Well, you couldn't reel it up.
Okay.
Okay,
Hmm.
so it just spit this
Oh, it
tape
just
out of
spit.
spit it out of the machine.
Oh, talking about
And
rat's
so we
nest.
had these huge garbage bins
Yeah.
that you'd put on the outside of the machine, and the tape would go
Just fly
into
into it.
that, just
Yeah.
right in there. And you could see it would come out of the machine, and as the garbage bag filled up, a
Yeah.
box filled, it would start to
Projectile.
go up
Yeah.
because there's back pressure
Right,
on the
right,
tape.
right, right.
And then you had to rewind it, of course.
Okay.
So we had
Oh,
these
so
very
they
high
would.
speed
Hmm.
film winders where you crank them, you know.
Hmm.
Well, what you did was you put the garbage bin across the room,
Okay.
and you started winding that tape, and because of course it would knot sometimes, and the
Right,
knot
right.
would come flying up out of the garbage bin. You have to stop the winder before and then you
Yeah.
could undo it.
But wait, if you had a knot in sort of towards the beginning, then you'd almost have to unwind it from, because
Yeah.
you wouldn't go from the other end, right?
No,
Sounds
no, no, no.
horrible.
It goes it well, you the front end was at the bottom.
Yeah.
So you were winding
Oh,
from
I
the
see.
back.
From the back. Uh-huh.
You see. So
Nobody
it
ever
was
nobody ever thought about putting the winder at the exit of the.
no, you can't. You couldn't.
Okay.
It was
Why?
moving too
Oh,
fast,
too fast.
and it
Okay.
was paper.
Okay.
So if you tried to wind it up, it would just rip the
It would
hell
just
out of
rip.
it.
Yeah, yeah. Actually, here's a random. I don't know if you knew this, but talking about ripping and sort of mechanics. Um, they limited the number of punches, because if you had too many punches, so they have a system. This. They have a
Yep.
system so that it wouldn't become too flimsy and rip. And
Right.
so which is a pretty, makes sense, but I would have never thought about it.
Well, we of course with the paper tapes. Remember I told you about the loader.
Yep.
There was a paper tape that had something on it called initial orders, which was basically the same thing as a loader,
Yep.
but it was a real short tape.
Okay.
Okay. And so the operators could shoot this thing through, and then they would wind it on an electric winder that they had on top of the machine. And they wanted the tape to be tight. So they would pull, they'd let some wind and then he'd pull it to tighten it.
Mm-hmm, mm-hmm.
Well, these were binary tapes. And so they would get
ripped.
They'd rip across.
Okay, yeah.
Okay.
Yeah.
So what the operators would then do would be to splice them with, they use transparent tape.
Okay.
Because it was an optical reader.
Right.
Okay, so that was fine.
Okay.
However, when the tape got ratty and you wanted to duplicate it, you took it in the back room and you put it on a flexowriter to duplicate it, and the flexowriter was a mechanical reader.
Huh. Okay.
So that meant that you'd get a tape that wouldn't work.
Okay.
Because the mechanical, of course, was blocked by the transparent.
The transparent tape. Yeah, that's right.
So that was a pain in the neck.
So was cards, are you saying that cards, card reader, was mechanical?
Card reader's mechanical, yes.
Okay. You'd have like little pins, and if it got pushed, it was read as...
Well, it was brushes.
Oh, brushes would make contact.
Brushes, yeah. There were brushes, and there was a conducting drum behind it.
Yes.
And so the brushes dragged across the card.
Yes.
And they would make contact at particular points.
Right. Okay, that makes sense.
It was also the case that a card reader would destroy cards in exactly the way that would prevent it from reading them. So there were basically two kinds of card readers that were in use when I was at CU early. Mm-hmm. One of them would pick the card from the bottom, sort of like the key punch. You know, the key punch would pick the card out and then you punch it.
Yeah.
And the other one would shoot the card in sideways.
Okay.
Okay, and read one read all the rows, the other read all the columns.
Okay. But the rows, you wouldn't get any information until you're finished.
No. Because it read the rows, and then it had a matrix, and it would read it out to the computer column-wise.
Okay, got it.
But the problem was that those pickers would, after a while, they kept working on the edge of the card, and the card edge would finally get to the point where it couldn't be read anymore.
I see.
Okay. Now, the one that read column-wise was faster, but it shot through, and when it shot through, it hit a
stopper.
A stopper, so that they could, so the card deck would come out. And so when it hit that, what did it do? It bunged up the end.
Right. And so
over time, the end would get so bunged that the card reader couldn't read it.
Oh, so interesting. So many, I love the, also coming from mechanical engineering, I love all the mechanical engineering of these, moving parts and, that went along with it. They're really symbiotic, right?
That's right.
That's pretty cool.
That's right. But of course, with the paper tape, you had to use an editor on the machine.
Okay.
In other words, you'd read your program up onto magnetic tape, and then you would edit it.
Yeah.
Because otherwise, you'd have to cut the paper tape and splice in new stuff.
Yeah.
And remember, we talked about these libraries?
Mm-hmm.
Well, in Sydney, there was a filing cabinet. And when you wanted a sign routine, you would go to the filing cabinet and take the paper tape for the sign routine out and duplicate it onto your program.
Oh, nice. Oh, so you'd have folders with things you could splice in. Oh, I love that.
There were folders. They're little file drawers because, of course, they were little
little spirals.
For these routines.
Right. Whoa, tape. That's pretty cool. So you wouldn't have to do the sign yourself. You could use. That's right. There was a library.
There was a library. Yeah.
Right. I mean, literally a library.
That's right.
Right. Yeah. Actually, it makes me think about, that's interesting it makes sense that historically it comes from, they're related, the words, right? We were talking about etymology. This is just a random side note, but we call CD, well, even okay, but CDs, let's use that
Right.
medium. We call them albums, right? We call them
Right.
albums. Well, that's because back when everything was 78s or 78s, vinyl, right?
Yep.
You could only fill an album with multiple discs, and they would put them. I have an album. Here's Aretha Franklin. I
Right.
have a little album. Anyway,
Right.
so random.
Right. And of course, that's where the term folder comes from.
Right. Oh yeah, the Manila folder kind of thing. And
That's right.
yeah, right.
Right.
Yeah, that's pretty funny to think about that. I love
Well, it's because you want to make the computer mimic what the human being thinks about.
right.
So if you talk about a tree of files, for instance, then people are going to say, "What the hell is that talk?" But if you're talking about folders and a few folders here,
Right.
and a bunch of folders, then people know.
Well, it's
And
interesting. Yeah, it's back to the sort of the point we were making earlier, where you're trying to make this usable. You're trying to make this amazing technology usable for the general public, right?
That's
Not
correct.
just the scientists or NASA or whatever.
That's right.
Yeah, that's really cool. So how did how does a processor, and also there's the AT mega. Here's my 6502. I got a 6502. So for those out there who don't know, this was in like Apple and Nintendo and Atari, Commodore 64. So or the AT mega 328. So how does it physically know, like you said, you put in an instruction like add two numbers from memory, but how does it know that the code is an add? Is it in the transistors, I guess, or in the silicon? It's
Yes.
okay.
Yes. It's in the logic.
Okay.
In other words, you have a bit pattern,
Right.
and that bit pattern, ones and zeros, controls gates, and those gates decode
Okay.
to a larger network, and then the quote architecture of the
Right.
machine
Right.
is able to interpret those bits
Right.
and carry out some function. Now, there are very few functions actually, if you think about it.
Okay.
I mean, we now have, of course, hardware arithmetic units. So that means that the instructions will be decoded by the control unit and pass their operands through the gates to the add unit, and then the result will be extracted.
Okay.
So that's all in the hardware of the machine.
And it just makes it more efficient to have an arithmetic unit rather than the general.
Well, yes, and actually, it's modularization.
Okay.
In other words, when you design your silicon, you don't want to have a sort of a random array of stuff that's going to be really hard to put together. So you want it to be regular, and so you allocate this part of the area of the chip to circuits that do a circuit that does addition.
Okay.
And then when you need to do addition, address arithmetic or arithmetic on the operands, you send all of that to the adder.
Okay.
So it doesn't matter whether you're adding the exponents of floating point numbers or the addresses of locations in memory, you're still using the same adder. And so you're reusing that circuitry.
Okay.
Okay. But you can then also build in software or firmware, if you will.
Right. Okay. So there's another buzzword, right?
That's right. And what that is it's a program which is a machine language program.
Right. And it's on the processor. It's in the
Yes,
processor's memory or whatever.
in
Yeah.
the processor's memory
Right.
or in fixed memory
Mm-hmm.
in the processor.
Where the process. Okay. Right. Okay.
So you may have several levels of instructions
Okay.
from the some very, very simple instructions to ones that are more complicated and so on. And another interesting thing historically was the IBM 360
Mm-hmm.
series was a whole series of computers that had the same language,
Okay.
assembly language, let's call it. It
Mm-hmm.
wasn't really assembly language, but it was close to assembly language.
Okay.
And depending on how much you were willing to pay, more of that was in hardware. Okay?
Because it's
So
faster.
that's right. That's
Mhm.
right. So a 360 Model 30
Okay.
was relatively cheap,
Yeah.
and there was a lot of,
you had to roll down the window manually.
well, sort
Yeah.
of. There
Oh,
was a no. You actually didn't see any difference in any program you wrote,
okay.
but there were levels of firmware interpretation
Mhm.
in that machine.
Yeah.
Now, one of the things that my wife did at Mutual of New York was she was responsible for a simulator
Okay.
for an IBM 650, which was a drum machine.
Okay.
Okay, no core memory, no solid state memory, but a drum that circulated around, and you wrote stuff on it and read stuff off it.
Oh,
That was the memory.
okay. So it
Okay.
was electromagnetic material.
Yes,
Got it.
just like a magnetic tape, but
Sure.
it was a drum.
Okay. All right. I'm with you.
Okay, so this is a drum machine, and ancient.
Yeah.
I mean, pre 1960.
Okay.
So she was responsible for a 650 simulator, which ran on the IBM 1410.
Okay.
1410 had a core memory and so on.
Right. So the
The
650 was a lower, like an older
It was
unit.
an older machine, yes.
And they wrote everything for that, and they got a new machine, and they didn't want to.
It wasn't that they wrote everything for that. But they had certain very important things that were written for that.
And they didn't want to rewrite it.
For various reasons,
Okay.
yes. We can talk about that later if you like,
Okay.
but
Yeah.
they didn't want to rewrite it. Okay, so she was responsible for that. So then we went to Australia. We came back after a year, and we had her boss over for dinner, slideshow and discussions, and we discovered that they were now running the 650 simulator.
Yeah.
On the 1410 emulator,
Okay.
which was running on a 360/50.
Whoa. Wow.
So here
What
was
a
two
level.
levels.
Yeah.
Two levels.
Wow.
And the program still ran faster than it did on the original.
But it seems like all that effort to write now. Simulate. Okay, we got to talk real. We'll say what the difference between simulator and emulator, because to me they sound the same in terms of functionality.
Yeah.
But it seems like if they're going to put that much effort to do that, you have to write the emulator or the simulator. Why not just write it for the new?
No, you don't have to write it. You look, let's say that there is a 650.
Okay.
And you want to get rid of that 650.
Yep.
Well, you don't think that you're the only 650 that exists, right?
Right.
Okay. So there are a lot of people with 650s who want to get rid of them.
Okay.
So IBM says, oh, you want to get rid of your 650? We can sell you an IBM 1410, and we have a simulator on it.
Okay. Wait, but I thought you said your wife wrote the simulator.
No, I said she maintained it.
Oh, maintain. Okay. All right. Got it. that makes sense. So,
right. and then when, in order to sell 360s, they had emulators.
Right.
And the difference between a simulator and an emulator is a simulator is all software.
Okay.
And an emulator is at least partially hardware.
When you say partially hardware, what is the hardware it would interact with? Or what is that?
The hardware, the emulator, if you write everything in software,
Mm-hmm.
then what you're doing is you would compile that program,
Mm-hmm.
and those instructions would run, and they would uh, manipulate the bits as though they had been hardware. But for every, say, add instruction, you would have to run 3 or 4 other instructions to load something and put it somewhere and do
Okay.
something with it, and then store it back.
Okay.
Okay. But the emulator has some hardware support, which means that instead of having to write every single possible state transition, if you will, in
Okay.
software, some of it was supported by hardware.
Okay. Okay. Yeah, that uh okay. Yeah, that's interesting. So what did your wife do when, again, back to the programmer?
Yeah.
Would you would again was it literally making punching cards and
Oh yeah.
yeah, okay.
Oh
All
yeah.
right.
Oh
Wow.
yeah.
So and so she would be entering the instructions.
Yes.
Oh, wow. Okay. And who would give her, I guess the company would just say we want this
Yes. Yes. That
task.
would be that.
Okay.
That's correct. Or
Okay.
they would say, look, there's something going wrong here, and it needs to be fixed. And so then she'd have to dig into the code and try to find out what was wrong, and so on.
Wow. So
Now,
what kind of numbers were they crunching? What kind of operations were they
oh,
doing?
this was an insurance company.
Yeah.
Okay, so that means that there are agents out there that are selling insurance.
Okay.
There are people who are putting in claims. There are claims that are being paid. It's a whole bunch of transactions. Okay.
Yep.
Now, all of these transactions are entered into computers
Right.
or on cards, and then translated to tapes, and the tape comes in,
Yep.
and every 24 hours they have to have processed everything that came in the last 24 hours.
Okay.
So that's the daily cycle.
Okay.
And the problem is that if the machine is a little bit too slow, or the number of transactions is a little bit too high,
Right.
then the daily cycle gets up to be 20 hours, 22 hours. And ultimately, it's something that you just can't get done
Right.
in 24 hours.
Right.
It's like the COVID overriding the hospitals.
Right.
Okay.
Right.
So then you have to get a new machine.
Right. Or
Or you have to do
a
something.
second machine or paralyzed or
Well,
something.
you can't really, because this is a sort of a sequential process. You can't.
Oh,
It's not a parallel thing.
okay.
All right.
Mm-hmm.
Now, there's been a lot of improvement now in financial software and so on, and a lot of things can be done in parallel.
Mm-hmm. At
But
this
when
point.
you have a sequence of things that have to be done in order, then you're stuck.
Right. Right. So what was your, it looks like you wrote some compilers.
I did.
So
I did.
what does that mean? So your job, you have a processor or a bunch of processors, especially if you're doing this intermediate language you were saying.
Right.
What your job is to turn, so really, again, your job is to turn human language into this
That's right.
intermediate language, which
That's
will
right.
then be okay.
That's right. Okay. Now let's be clear here.
Yep.
That is that I have been an academic
Mhm.
my entire career, basically. It's been an academic career.
Right.
So what I've been interested in is, how do you do these things?
Okay. Okay.
Okay.
Uh-huh.
Yes, I've written compilers, but my primary interest in is how you do it, and can you automate it?
Can you automate
Can you
the
automate?
compiler?
No. Can you automate the production of the compiler
The production of the compiler. Okay.
so that you don't have to write every instruction in that compiler yourself?
Okay.
Okay.
Got
now let's look at what a compiler does. The first thing it does
and can I say the compiler is totally software? It is not. I mean, arguably it's on a but it's not, right. It's not going to be on the AT Mega. It's on my laptop.
That's right.
Yeah.
That's well. It resides somewhere, but it is software.
Right.
So it's a sequence of instructions.
Mm-hmm.
So the first thing it has to do is it has to read the text of the program. And it breaks that text up into what are called basic symbols. An identifier, the name you use for something, name for a variable, the name for some place to jump, whatever.
Yep.
Those are all basic symbols. Okay? So the process, which is known as lexical analysis, breaks that text up into a sequence of basic symbols. Then, of course, what is a sequence of basic symbols? Well, they make up expressions. Mm-hmm. They make up various constructs, data definitions, and so on. And so you have to establish what the structure of that sequence of basic symbols is.
Okay.
That process is called syntactic analysis.
Okay.
Because you're looking at the syntax of the programming language. Mm-hmm. What results from that is a tree.
Okay.
A big tree.
A decision
represents
tree?
The entire program. You can think of what an expression tree looks like, and the whole program tree is just somewhat more complicated, but it's the same kind of thing. It's a single tree.
Okay.
All right. Now, you have used identifiers to represent concepts, a variable, an integer variable. Mm-hmm. Well, we have to decide if you wrote I here and if you wrote I there, was that the same I? Did that refer to the same concept? Mm-hmm. No, not necessarily, because you can structure your program with procedures and blocks and compound statements, which allow declarations within them. Okay, so I, the symbol, the identifier I, may have many meanings. And it appears all over the tree with different meanings. So there are two processes that lumped together are called semantic analysis. You're trying to find out what the semantics of this structure are. The first of those two is name analysis. And that's what says, oh, this I and that I are the same I. And the second process is type analysis. Mm-hmm. And that says, oh, this I is an integer. It's an integer I. Mm-hmm. And so when I do an addition of this integer I and this integer j, I need to use an integer addition instruction.
Okay. Yeah, right.
So you assign a type to each entity.
Right.
Okay, now we begin to get into the language problem because the language may have dynamic types. It may have types that can only be determined at runtime. So this has to be sort of put off to a library.
Right.
But basically the compiler has to figure out essentially what is this program.
And the output of the compiler is a list of
No, wait.
Okay.
We have a tree.
Okay.
And we've decorated that tree by saying this I and this I are the same, and this is I is an integer I, and so forth and so on.
Yeah.
And now we have to produce some output.
Right.
Now, question, what would you like as output? We could produce assembly language.
Right.
We could produce byte code.
Mm-hmm.
We could produce machine language.
Well, what's the difference between byte code and machine language?
Byte code is interpreted.
Okay.
So it's a sequence of bytes that are not machine instructions,
but they can be interpreted to.
They can be interpreted by an interpreter. It's like the old business with the 650 interpreter, right?
Okay.
The 1410 code isn't 650 code. All right.
So just
the 650 program has to be encoded in
right
characters.
So you have all these options, and it just depends on where it's going and what.
That's right.
Yeah.
That's exactly right. Depends on where it's going and what you want.
Right.
Okay.
Okay.
And so once you've got this decorated tree,
mm-hmm.
then you do what you want with it.
Right.
Now, currently, in many, and I would say that this is true in the Arduino, but in many applications, you have a C compiler,
mm-hmm.
which translates into an intermediate language. It's not a byte code. It's a language called LLVM.
Okay. Are you familiar with
low-level virtual machine?
Low-level virtual. Are you familiar with GCC?
Yeah, GCC
is that what it does?
That's one of the. GCC is very, very flexible.
Oh, okay.
GCC is actually a suite of tools.
Okay. Got it.
Compilation tools. Yes.
Got it. Okay.
Okay. So the C compiler will take this tree and turn it into a sequence of machine-like instructions.
Okay.
But then those machine-like instructions are going to be optimized for the actual hardware.
Right. So you're going to have some kind of pre-processing that tells the compiler what the hardware that it's going to, kind of. Or some kind of flags, or I'm not sure.
Yeah, that's right. Yeah, okay. That's right. You have some command line options, or your IDE takes care of it, or whatever.
Right. Okay.
Right. But this LLVM is one of the modern incarnations of a thing called UNCOL.
Okay.
UNCOL, called the Universal Computer Oriented Language.
Okay.
Now, this was actually was postulated in 1954, very early in the game. The problem that it addressed was, if you have N languages and M machines, you have to write N times M compilers, one for each pair.
Right.
However, if you take those M languages and machines and separate them and put one language in the middle, then you have to write from each one of the languages to this intermediate, and from this intermediate to each one of the machines.
But every company that was making these machines had to agree to do that.
Yes, and it never actually got done.
Oh, okay.
Well, I won't say it never actually got done, but it didn't enter the mainstream until Java.
Oh.
And that was the function of the bytecode. You translated Java into this bytecode, and then you translated the bytecode into the various machines that you wanted it to run on. Okay, so that's the first step. Then you got some other people who said, hey, this bytecode is interesting. Why don't we translate our language into this bytecode?
Right.
And now you have that situation where you have a bunch of languages, bunch of machines, and the JVM in the middle.
Huh.
Okay. And then, of course, Microsoft came up with C#,
mm-hmm.
and another sort of intermediate language, and LLVM. I mean, there are now a number of them which fulfill this function, more or less. The problem is that if you use one language,
mm-hmm.
then you can't take advantage of special relationships between a language and a machine architecture.
Right.
because they all have to go through this filter.
Sure. And if that filter is not, doesn't have the breadth or the every piece, yeah, exactly. And it won't.
Right.
Yeah.
It won't. And so in terms of the JVM, the first implementation was an interpreter on each one of these machines.
Mm-hmm.
Now we have what we call just-in-time compilers,
Okay.
which take the JVM code and do a lot of optimization and so on for a particular machine.
Okay.
So that although initially Java was not particularly efficient, in other words, you wrote a Java program, well, it ran a little bit slow.
Yeah.
Especially compared to a C program. But now, with the JVM and the just-in-time compilers and all the optimization there, Java programs will run just as fast as C programs.
So you think, I remember hearing that Fortran is still around not only because of legacy code that nobody wants to, turn into C, for example, but also that it's faster. Is that true? Is that therefore today C is comparable to Fortran then in terms of speed? Is it, or was my statement even correct?
Okay. Again, we have to look a little bit of history.
Okay.
Fortran the name Fortran comes from formula translation.
Okay. And
the purpose of Fortran was to wean scientists away from assembly language. Okay? And in order to do that, the designers of the language felt that if there was a single problem which was suitable for coding in Fortran, and yet which could be implemented faster than the Fortran compiler, they would have failed. Okay? They were trying to convince people not to use assembly language, but to use this higher level language.
Right. But there's no way, but just since it's higher level, there's no way it's faster than assembly.
You'd be surprised.
Okay.
The Fortran, if you look at the early versions of Fortran, they are very close to machine language in the sense that the only things that they allow you to do are things that the machine will do.
Okay.
For example, for a long time in Fortran, they didn't have mixed mode expressions. You had to either write an integer expression or a floating point expression.
Oh, you couldn't multiply an integer by a floating point.
That's right. That's right. And also for a long time, array references, the subscripts, had to be linear. They had to be constants, sums of a variable and a constant, or something times something plus something. But that was it. You couldn't write normal, any old expression as a Fortran subscript.
Okay.
The reason for that was that those things could be optimized.
Okay.
And those, if your program respected this initial Fortran, then it would run as fast as the assembly code equivalent.
Okay. But of course, much more readable.
Of course, much more readable and fewer errors.
Right. Yeah, that makes sense too.
And the problem was all they had to do was to get the people off assembly language.
Okay.
And once they did that, then people realized, wait a minute, my costs are in writing the code, not in running it. There are very few applications where the runtime is a significant thing.
Okay.
Now, I'll give you an example of one. One of the people we knew from college went to, I think it was MIT, and he was doing numerical stuff. What he was doing was what's called Monte Carlo simulation.
Absolutely. Love it. Absolutely.
Okay. Well, if you think about that, that comes down to the random number generator.
Mm-hmm.
If you can improve the random number generator by writing it in bits,
Mm-hmm.
you can save a tremendous amount. This guy would come.
Save tremendous amount of time.
Yeah.
If your random number generator is faster.
Yes. Now
Okay.
but let me set the stage here. This guy would come down from Boston to New York with a single punched card.
Okay.
He would go to the IBM data center downtown.
Yeah.
When the people, stopped using it at midnight or whenever it was.
Yeah.
It was a 7090, an IBM 7090, which was a pretty darn good machine in those days. He'd put the card in.
Okay.
And then he'd sit down and twiddle his thumbs. And when the systems engineers came in the morning, he would say, "Oh, you need the machine? Right. Push a button." Machine would punch out one card.
Okay.
He would take it back to Boston until the next time he came down to New York.
Okay.
Now, if you could improve the random number generator by 10%, you would have taken 3 months off the time he took to do his thesis.
Oh, wow. Wow. So he was literally just using the random number generator.
Yeah, he was, what he was doing was he was simulating a cross section of a nucleus or an atom or something like that.
Okay.
And he was using Monte Carlo simulation.
Yeah.
And as you know, that comes down to generating a boatload of random numbers.
Right. And so he would just sit there. Yeah. Yeah.
So it's
wow.
But my point is that random number generator is maybe 15 instructions. You can spend the time on 15 instructions trying to make them better.
Yeah.
But you can't spend the time on the daily cycle for Mutual of New York.
Right. Right. Yeah, that's really cool. Huh. So back to the Arduino.
Yes.
So when you hit compile, so it goes through the compiler, turns it into probably intermediate. It's probably using GCC. I could look into it, but it's probably using, and it's, and then of course the settings for the flags, they're all in the IDE. They're all taken care of, right? Because you're using it. And so then it's optimizing, and it's got this, and then it spits out this intermediate language. But then it immediately, because we don't see any of this, right? So it must immediately go from the intermediate to
yes, and it's another processor. So nowadays, how do you make a distinction between a compiler and assembler?
Yeah.
The assembler, in my mind, now this is me. This is me talking.
Yeah.
What the assembler is going to do is it's going to replace symbolic machine instructions with their binary equivalent, which is just basically a table lookup.
Yep.
And it's going to replace symbolic addresses with their actual addresses.
Okay.
And that's it.
Okay.
Won't do anything else.
So in essence, so it'll go through the compiler, and you're saying then it goes through an assembler.
It has to be assembled at some point.
Yeah.
The assembly process, the addresses have to be fixed.
Right.
Now, fixed is, again, because you have relocatable code, which is, some of the addresses are still not fixed because it depends on where you're going to load it in memory. And that is also a sort of a part of the assembly process. So in some sense, what you're doing is you're deferring part of the assembly process to load time when you actually load the stuff into the machine.
Now there's also this linker, but I think that's a C code. That's specifically software, right? That links different C functions. So I don't think that.
No. Now, but be careful. The
Okay.
linker
Yeah.
is the thing that actually provides the last phase of assembly.
Oh, it does. Oh, okay. Okay.
Sure. Because when you're linking those guys together, what are you doing? You're putting them into the same address space.
Okay.
And so that means all of their addresses are going to change depending on where they are put in the address space and what's before them and what's after them and so on.
Okay.
So that's where the assembly process is done.
Okay.
The last step of it.
Yeah.
See, you can do it piecemeal.
Okay.
Within one of these routines,
Mhm.
it's relocatable. It has been assembled into these relocatable addresses.
Okay.
And then the linker
Cool.
does the final
Okay.
step.
So compiler, assembler, linker.
Compiler, assembler, linker. Yes. No, those are the processes.
Okay. Okay.
And it may be that those processes are divided among various programs in what we now call the tool chain.
Right, the tool chain. Right, which I've seen. So why do you think there are coming up and programming? Why do you think there are so many different languages? I mean, do you have a take on that? I mean, I don't know, in the sense that, right, it's Fortran and then there's Java, then there's C. Why is there just a big picture reason for all that? Or is that too complicated of a question?
No,
I'm just thinking of the languages too.
No, it's not too complicated at all. I mean,
or is it just that part, or I'm just thinking here, but is it just that people just came up with different things they liked in it?
Yes, that's certainly part of it.
Mm-hmm.
Language is a religious issue.
Okay.
You have people who, well, back in the day, there was a lot of dissension about whether you should write in Fortran or in C.
Oh, interesting. So C, I was thinking C was much newer than Fortran.
C is much newer, but
okay.
Fortran has been around. An interesting comment. I was participating in a course on software engineering, and one of the lecturers was from Britain, or actually he was a Brit, but he was working in France. Yeah. And the question that was posed to him, this was back in when was it? It must have been 1980s. Somebody posed the question of what will the language of 2000 be?
Okay, yes.
And his answer was, well, I don't know what it'll be, but it'll be called Fortran.
Interesting. Okay.
Well, the Fortran language is, it's been developed over the years. It's gotten things from other languages put in it. If you look at C got object-oriented programming into C++, or C# for us. I mean, all of these languages had let's call it an ecological niche.
Okay.
COBOL.
I've heard of that.
Business.
Okay. Right? Yeah. It's kind of like R. It's kind of like R is for statistics, where MATLAB, and that is for engineering. I don't know. It's kind of like that. Maybe.
Yes. Okay. What you've got a number of languages that reflect the languages that the users use and that they use in their
country, from their country.
Well, yes, from their country. That's right. Numerical analysis or artificial intelligence or blah, blah, blah. Yeah. So it's just like it is in the world of natural language.
Right. Yeah. Okay. All right.
And it's also what you learn. It's interesting that an ongoing debate in computer science is what should be the first language of programming.
Right. Python, for example, you mean, or whatever?
Python or C or Scheme, or and there are as many arguments as there are
Oh yeah, I
computer
mean we
science
have the
departments.
same argument right now in mechanical engineering. We're like, should we teach Python instead of MATLAB, for example, in our numerical methods class?
Right. And you all have reasons why this is good, and you
Hmm.
probably have a robust debate going on.
Yeah.
But one thing we've learned is that often the person programs in their first language forever, no matter what language they're
Mm,
programming in. So a person who learns C first is going to program Java as though it were C for a long time.
right.
Think of basic.
Joe says, think of basic.
Yeah. Go 220.
Yeah,
Yeah.
yeah, yeah. And it's hard. You
Hmm.
get a paradigm in your head
Right.
for how you approach a problem,
Right.
and it's hard to change.
And therefore, you might not take advantage of the
Correct,
new language, even if you're programming in it.
correct.
Hmm.
And that, if you think about it, that is an advantage of a system like the Arduino, which
Hmm.
doesn't really let you do much.
Hmm.
They want you to state that problem on the highest possible level.
Yeah.
And so you don't really care what's underneath
Right. Until you do.
until you do.
I got
Yes.
one example I've I think about in that vein is I've run a motor with this, and there's it has a command called analog out, but it's actually not analog out. It's actually a pulse width modulation. They call it so they're hiding the like it acts analog if you pass it through a low pass filter, right? Because you get the DC. But anyway, so or you can send it out to a motor because the motor will low pass it to the DC term anyway. But it's I think the Arduino, it's a set frequency. Like the pulse width is what changes, but the frequency set. So it's set to like I could Google it, but let's say it's 350 hertz. Well, that's audible. So here you have if you're doing a motor, right? If you're that motor becomes a speaker. So you have this really annoying, 350 hertz, and I'm like, where is that? So this is a reason now I've gone down and I'm like, I'm not doing this anymore, and I've gotten into it and been able. You can change it, right? But you just have to, as they say, code to the metal.
Yeah. Yeah.
But anyway, that's just an example of.
Yeah. Well, that's actually pervasive. The one of the big things in aircraft now is something called automation surprise.
Okay.
When the automation does something that you as the user don't expect.
Yeah. Yeah.
And for your people who might have any interest in aviation, there's a fascinating video called "Children of the Magenta Line."
Okay, I got
exactly about this
automation
problem.
surprise. I love that. I mean, this is part of my argument of having this conversation is because as much as the Arduino is amazing, I find that well, there's a lot behind the curtain, right?
Yes.
Ignore the man behind the curtain, right?
Yes.
And at some point you may need to get behind the curtain and do something like that.
Right. You may need to. And the suggestion, of course, is to try to fight that in the sense that make darn sure that you really need to.
Right.
Now your 350 hertz, that's a really need to. I mean, it's something that's annoying, basically annoying.
Yeah.
Or there's something that just doesn't work because of something that's in there.
Right.
In that case, yes. But if it's a matter of saying, oh, I could make this work a little faster, don't bother.
Yeah. Yeah. Well, but for my uses, for example, if you're doing control,
yes,
now
of course.
Now you need to run this code within a certain
Yes,
delta t,
that's
and
right.
that could cost
You're
you.
you're absolutely right. You're absolutely right. You must do it, then do it.
Right. And that's my world is
Right.
I must do it.
Okay.
Yeah.
Well, then you need to know a little bit more.
Yeah, exactly. Which is why this has been an awesome conversation. I loved hearing the history. This was fun.
Okay.
I hope did you have fun?
Oh yeah, sure.
Okay, good. Awesome. Thank you so much, Bill. I think we're in a good place.
Okay.
And we've been talking for, what is it, an hour 20, I think, at this
Something like
point.
that.
Yeah. So
Yeah.
now I got to figure out how to parse this thing to be edible for
Okay.
my students.
Okay.
Yeah.
Well, whatever. If you need any help in the future, let me know.
Yeah. Awesome. I really appreciate your time. This was a lot of fun.
Okay.
Awesome, Bill. Thanks a lot. I'll see you a little bit later.
Yep.
Actually, let me just stop the video here. Let me just